Hello, everyone, and welcome to today's lecture in the series Reasoning LLMs from Scratch. In the last lecture, we looked at the policy gradient theorem, which told us that the gradient of the performance measure of the policy is directly proportional to the state distribution, the action value function, and the gradient of the policy. We also looked at this gradient does not involve the gradient of the state distribution itself, which might have been very cumbersome to calculate. And this allows us an easy way of calculating the gradient of the performance measure itself. In today's lecture, we are going to build upon the policy gradient theorem and look at our first algorithm in which we are going to use the result of the policy gradient theorem, our expression for the parameterized policy, and the gradient ascent algorithm to find out the policy parameter which maximizes this performance measure. Let's start with our first policy, which is called as reinforce. Now remember that in the gradient ascent method, what we saw was that we, let's say, start somewhere around point A, which is not an optimal policy, and slowly we want to ascend along the direction of the gradient and move slowly and steadily towards point B. And every step of the way, we are going to update our policy parameters towards the direction of the gradient at that particular policy step. So, for example, here now theta t is the policy parameter at the current time step. We are going to say that the policy parameter at the next time step is theta t plus alpha times gradient of the performance measure, which will ensure that we are moving towards the direction of maximum performance measure. Now, here, the policy gradient theorem tells us that this gradient is proportional to the summation of the state distribution for all the states, summation of action values for all the actions, and then multiplied by gradient of the policy. Now, what we had neglected in the last lecture was these summation signs, which we are going to focus in detail in the reinforce algorithm. So this summation sign means that summation over all possible states, and this summation sign means summation over all possible actions. And now we are going to simplify this expression using some concepts in probability, which I'm going to explain below. The first concept is that of expected value. So let's say we have a random variable x, and each possible outcome has a probability of p of x. So then the question is, what is the expected value of this random variable x? The formula for the expected value can be written as p of x into x or x into p of x. The expected value, when given by this expression, gives us if a random variable happens and we know the probability of every event of that random variable, then we can find out the probability, the entire probability of the event. Let's say I roll a dice and every single face value has a probability of 1/6. I ask you what is the probability of the event. So what you will do is you will say 1/6 into 1 plus 1/6 into 2 plus 1/6 into 3 plus dot dot dot. So you will multiply this and then you will tell me which is equal to 1/6 of 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is equal to 6, 3 plus 6 plus 4, 10, 21. So this is the expected value, which is 3.5. So in a similar way, expected value of uh, any random variable can be calculated if the probability of every event in that random variable is known. Similarly, we can, if you replace this x with p of x, with f of x, we can calculate the expected value of f of x also by multiplying the probabilities of each event not by x but by a function of x. Now what we are going to do is that we are going to consider this expression, which is sigma mu of s into y of s. Uh, Now mu of s is telling us what is the probability of the agent being in that state. Remember, this is the state distribution, and if we have values of S1, let's say there are four states, and every state is visited, maybe this is 5 times, 10 times, 15 times, 20 times. So then mu of S1 is equal to 5 divided by addition of all these, which is equal to 20, 50, which is 1 by 10. Mu of S2 is equal to 10 divided by 50, which is equal to 1 by 5. Mu of S3 equal to 15 divided by 50, and mu of S4 equal to 20 divided by 50. So these are nothing but the probability of the agent reaching that particular state, and we have multiplied that with a function of the state, which is very similar to this expression. You see, p of x into f of x. Here p is replaced by mu and f is replaced by y. So this can be written as expected value of y of s, and hence the above expression in the policy gradient theorem can simply be written as expected value of whatever comes inside. So basically this is y of s now. So it becomes sigma mu of s times y of s, which is equal to expected value of y of s, which is the expected value of whatever comes inside. So what you essentially say is that you say, okay, you I want to remove the summation of all the states outside this equation, and I want to say that this expression is equal to the expected value of the summation over all the actions multiplied, and then inside the summation we have the action values and the gradient of the policy. So this is how the policy gradient theorem can be written as. Now, how can we write the update rule for the policy? Remember, the update rule was given by theta t plus 1 equal to theta t plus alpha times gradient of the performance measure. And we just saw that gradient of the performance measure can be written as like this, which means that the quantity inside the expected value, which is sigma a q pi of s comma a grad pi of a given s comma theta. This is this is a distribution whose expected value is equal to the expected value of the performance measure, which means that we can directly use this as a proxy for the gradient itself. And this is what we are doing over here. Uh, it's You might be thinking, where did the expected value go here? I'm not writing the expected value here anywhere. The reason the expected value is not coming is in the policy or in the gradient ascent theorem, uh, we have gradient of j of theta. Now this can be replaced by, let's say, another function mu of theta only if the expected value of this is equal to grad of j of theta. And we did get that expression, expected value of this is equal to grad of j of theta. That is why we were able to replace the gradient with this value. And now the update rule for the policy parameter can simply be written as this, where we write theta t plus 1 equal to theta t plus alpha times summation of, notice that we have written q hat here, which is the approximate action value function, and we have written w here, which are the weights. So if I am at a particular state and there are five actions I'm seeing in front of me, what I will do is I will calculate q hat for all of those actions, and then I will take a summation and I will multiply it by this grad of pi a given s comma theta. Now this is something which is an algorithm which is used in some cases, but it's not very practical because summation over all the actions, it's a bit difficult to do. Ideally, I don't want to sum over all the actions. I only want terms in my policy update rule which involves the current state and the action which is taken at that state. I do not want to include the summation over all the actions. So, how can I modify the expression above by without involving summation over all the actions? Remember, we have done something similar above. We have replaced summation over all the states by the expected value. And now we want to get rid of this summation over all the actions. So there is a mathematical trick which is used to do this. So before this, what we had obtained was the gradient of the performance measure is proportional to the expected value of summation of a q pi s comma a into grad pi. This is what we had written over here. Now, let us see if we can absorb the summation of actions also into the expectation, just as we did for the summation of states. And for this, what we are going to do is we are going to take this expression and we are going to multiply and divide by pi of a given s comma theta. So you can see that this expression is same as this expression. The only thing we have done is in the numerator we have pi of a given s comma theta, and in the denominator we have pi of a given s comma theta. Okay, so now why do we do this? Why do we multiply and divide by pi of a given s comma theta? The reason will become clear in a while. So whatever we see in this red brackets, it says pi of a given s comma theta into q pi of s comma a. Now in the concept one, what we had looked at was expected value of f of x is equal to summation of x into f of x into p of x into f of x. This is what expected value of f of x was. Now this is something which looks kind of similar. This is the probability and this is the function. So if you multiply the probability of an event by some function which depends on the parameters of that event, then you get the expected value of that function itself. So this entire summation sign can be replaced as expected value of q pi of s comma a for that given policy pi, and then you can rewrite the above expression as like this: expected value for the policy pi into q pi of s comma a multiplied by gradient of the policy divided by the policy itself. And we can do one more step after this. Remember that q pi of s comma a is the summation of all the rewards which the agent gets after selecting an action A for a state. So this is nothing but expected value of the expected return, which is denoted by g of t. So essentially, you can replace uh, this q pi of s of a by the expected return itself, which is g of t. So I understand that this is a bit mathematical. I will again explain this, but let's go to the final policy update rule, which is written over here. Finally, we get theta t plus 1 is equal to theta t plus alpha times expected return into gradient of the policy divided by the policy itself. Now, this expression is something which we are going to understand later as well. But before, we have used some concepts of probability to arrive at this expression. Only concept number one is used in. We have used that concept two times. First for approximating over summation of states, and second for approximating over summation of actions. So when we approximated over summation of actions, this pi into q pi got absorbed as q pi, and then we looked at if you take a Monte Carlo return and the expected value of that Monte Carlo return is the action value of that state and action pair, so you replace this expected value of q pi of s comma a by the expected value of g of t, and then this is how the policy parameter update rule can be written as. Uh, in case the probability concepts are not clear, I would like you to again go through this derivation by yourself. And the reason I ask this is because whenever we see this type of expression, grad pi divided by pi, it is something which we are going to encounter frequently in the policy gradient lectures. Even in PPO and GRPO, you can see the way these terms appear are exactly like this in all the expressions. And whenever you see a term which is grad pi by pi, you should immediately connect it to, okay, this is related to the gradient ascent theorem, which we had looked at in the reinforce algorithm. So it should not be highly intimidating for you, but you should think that, okay, whenever we take a gradient of the performance measure with respect to the policy parameter, we get a term which is proportional, or which is given by gradient of the policy divided by the policy itself. Okay, so now this is the expression that we have got. So practically how we implement this is, let's say I'm an agent and I'm going through multiple states. At a given state, I take an action of that state for that particular state. Then what I do is I can immediately calculate this expression because this is given to me, a given s, and this is also given to me. But I have to wait till the end of the episode before I calculate g of t. And then once I calculate all of this, I substitute in the expression and I update my policy parameter, and I do it for every step of the way. So this is how the policy parameter is updated, and we keep on updating this parameter till we maximize the performance measure. So this is how the algorithm of reinforce works, which is our first policy gradient algorithm, which we have looked at. Now the intuition behind this algorithm is very unique, and we are trying to build that intuition. So let's say the agent is in state S and takes action 80, and the agent learns or earns a total reward of g of t. The question is, how do I update the policy parameter now? We definitely have to use this formula, but how does that look like in terms of vectors? So let's understand. So we are at this point O, which is our old policy. Our old policy is given by two parameters. In fact, all our policies are given by two parameters, theta 1 and theta 2. So we are over here right now. And we are going to move in the direction which maximizes the performance measure. And this direction is given by grad of pi 80 given st comma theta divided by pi of 80 given st comma theta. So this grad pi actually gives the direction. So I am going to move in the direction of grad pi of 80 given st comma theta. Now what does this direction signify? This direction tells me there are a lot of directions I can take in this point. Oh, I can either take this, I can take this, I can take this. Why only this direction? Because if I move in this direction, then whenever my agent is in state st, it will maximize my chances of selecting action 80 for that state. Remember, that is what policy does. Policy means that what is the action I have to select when I reach a particular state. So when I am moving in that direction, I am maximizing my chances of selecting the action 80 when I am in that state. And there is a factor of g of t here, which means that if the reward I get is very low, then why do I need to move so much in that direction? I will not move in that direction because I do not want to select action 80 when I am in the state. So that's why it's multiplied by g of t. And the reason it's divided by pi is because we want to give, we don't want to give too much importance if the agent keeps on visiting that particular state. So if the agent keeps on visiting a state a lot of times, then g of t into grad pi will keep on increasing, increasing, increasing. And the reason it increases, it's not because g of t is higher, but the reason it increases, it's because my agent is just reaching that state more number of times. So I will penalize that. I will penalize the amount of times my agent is reaching that particular state, and that is why it is divided by this pi of at given st. So that is why it is divided by this pi, because I want to penalize. I don't want to give importance to how many times my agent has visited a state. I only want to give importance to what is the reward I'm getting, which is what I multiplied by, and I want to move in the direction which maximize the chances of selecting action 80. This is the intuition behind this formula. So even if you are not comfortable with the mathematics, it's all right. Just remember this formula and remember the intuition that is associated with it. So there is a very nice activity over here which we are going to look at. This will help you understand visually how it works. So currently this is where I am at theta 1 and theta 2. The red arrow represents the gradient direction. Remember, the gradient direction is grad pi divided by pi. I think previously I said it's only grad pi, but it's grad pi divided by pi. And the blue arrow, the blue contours are the action probability landscape. So what we are going to do is update each step and see how my agent moves. So you can see that at every update step, whenever my agent goes and updates, the the red curve, which is the direction of the gradient, it keeps on changing. So here we have fixed a g of t, but in reality the g of t is different for every step. So basically, the way these theta are updated is theta t plus 1 is equal to theta t plus alpha times g of t grad pi divided by pi, which is exactly what we looked at before. So depending on the direction, the agent moves either up or the agent moves down if the direction is positive or negative. So this is how the reinforce algorithm is used to calculate the policy parameters which maximize your performance. From this visualization, I only want you to understand how at each step theta 1 and theta 2 keep on varying. Uh, and depending on the values of theta 1 and theta 2 and the gradient direction, the next values are updated based on grad pi divided by pi. That's all. Okay, so now once we have understood reinforce, the next algorithm which we are going to look at is a derivative of the reinforce algorithm, which is reinforce with baseline. So what reinforcement with baseline says is that uh, what if we subtract a quantity from g of t? We keep the entire update rule the same. The only difference we do is that we subtract this quantity b of s from the Monte Carlo update rule. So, from this reinforce update rule, if we subtract a quantity b of s, what will happen? So the reason this quantity is subtracted is because if you do not have b of s, then there is a lot of variance, as we looked at over here. The variation is very high. So to reduce this variation, there is generally a parameter which is added, which is subtracted from the total return, and this parameter is g of t minus b of s. The only reason this bias is introduced is because we want to reduce the overall variance of our algorithm. And a natural choice for this is the approximate value function, which is v hat of s comma w. So this is the update rule for this algorithm, which is reinforced with baseline. And the only difference from reinforce is there is a common term which is subtracted from the return, and this term can be any function of the states. it should not have actions here, because if it has actions then we cannot use it in the formulation, since it will depend on the gradient, so we cannot take it out in this formula over here. But if it only depends on the states, then it can be safely used. So this is how the update rule becomes. Even in some modern algorithms like PPO and TRPO, there is a variation of this which people use, and there is a baseline which is often added for ease of for reduction of variance in the final calculations. But for our understanding, we should only remember that this uh, bias term is mostly the approximate value function for that state. If you remember what v hat is the uh, approximate value function which is represented by the weights. So it's the approximate value of the expected return which the agent is supposed to get from that particular state till the end of the episode. Okay, and the last algorithm which we are going to discuss today, which is included in the policy gradient methods, is the actor and the critique method. So, why the name actor critic, and what's the formulation like? So, in the actor critic method, the only difference we use is that, remember, this g of t is the summation of all the reward which the agent gets from a particular state till the end of the episode. So I cannot update my policy parameter until I reach the end of the episode. And we had encountered this exact same problem when we introduced temporal difference learning over Monte Carlo learning. And there we looked at the way to solve this is that we can replace g of t by r of t plus 1 plus gamma times the value function estimate of the next state, s of t plus 1 comma w. Now, this is an approximation of the return which the agent encounters throughout the entire episode. And we have been coming to this approximation. I think we have come to this at least 8 to 10 times in this reinforcement learning phase. So by now you should be clear that this is a temporal difference target. And instead of the Monte Carlo target, we use the temporal difference target over here. And this is the actor critic method. What happens is that this target is the actor and this target is the critique. So the the critique is the function which is the bias or the baseline, like we saw in reinforce with baseline, and the critique is subtracted from the actor value. So the reason it is called actor critic is not very straightforward. I think the reason it's called actor critic is because the actor is the one which is producing the actions. So whenever the agent is taking an action, it is receiving a reward r and it's going to the next state whose value is given by v of s t plus 1. And since we are subtracting it from the critic, it's like someone is criticizing that action. So that is why it's referred to as actor critic. So whenever you have two terms a minus b, this A is the one which is producing an action, getting a reward, and then getting a value of the next state. And B is the value of the current state, which is the critique. So it's like whenever you are in a position and you advance and go to a new position, you look back and you say, what is the value of the critique? And you do a difference between the two. So this brings us to the end of the algorithm. So in today's lecture, broadly speaking, we discussed about three algorithms. Firstly, reinforce, second, reinforce with baseline, and third, actor critic methods. In the reinforce, we developed a very nice intuition about the way in which the policy parameters move. They move in the direction of the gradient, which is given by grad pi divided by pi, and we multiply that by a function by g of t. And the reason we multiply by g of t is because we want to uh, favor actions which are producing more rewards in the future. So the direction is giving me, if my policy is moving in this direction, I am maximizing the chances of selecting that action. But if my return is low, then I do not want to maximize the chances. So that is why we multiply it by g of t. So we multiply by g of t and then we move in that direction. So finally, we keep on doing this process until we maximize the performance measure. Now, the other two policies are variations of this of the reinforced policy, and what they say is that, okay, don't just consider g of t, but subtract it from a baseline, which is the approximate value function, to reduce the variance in your policy updates. And it has been shown to significantly reduce variance, so it is commonly used in practice. And in the actor-critic method, the target is replaced by the temporal difference target, which is the summation of the subsequent reward and the discounted value of the next state. So this becomes the actor, and then we subtract it from the critic, which is the approximate value function for the current state. So this brings us to the end of the lecture. There are some mathematics here we have discussed, which some of you might think it is slightly complex. I have made my best effort to explain the mathematics. If you are still not clear, then please revisit the expected value concepts which I have described in this lecture, and then the mathematics will be clear. Otherwise, the intuition will always stay with you, even if you don't remember the maths. So now in the next lecture, we will slowly move on to algorithms like TRPO, PPO, and GPO and GRPO. Thank you very much, everyone. Bye.